Now let's look at this question. It's question number 1. The input of a 6-pole, 3-phase, 50 Hertz induction motor is 50 kilowatts. That's the input power in at a speed of 970 RPM. The stator losses are 1 kilowatt and the friction and windage losses are 1.6 kilowatt. Calculate the following: the slip, the rotor copper loss, the output, and the full load efficiency. So you must write down the parameters that is given. So now, since the power into the motor is 50 kilowatts, right? Now, the power goes into the stator, right? Now, in the stator, we are told that the stator loss is 1 kilowatt. So which means the iron loss and copper loss on the stator is 1 kilowatt. All right. And we're also given that the friction and windage loss is 1.6 kilowatt on the rotor. You can see that I've split this into 3. The first line is your stator line. Okay, so this one first here is for the stator. And this is for the rotor. And now here is for the shaft. Okay, I'm sure you know. So this is a shaft. This is your shaft. Okay, that's a shaft. Our shaft is this. So because now the power that will make this to rotate like that, all right, on the shaft, if these bearings are not properly oiled or lubricated, then there will be some friction losses that will try to hinder this from rotating faster. Okay, so we need to really remove those losses. Okay, so that means I have grouped this into 3. I have the stator, I have the rotor, and I have the shaft. This is a shaft. So we have those 4 parts: the stator, so which is that, the rotor, which is this, and then the shaft. So on the shaft, I need to I need to indicate the friction and windage loss, which is given to us as 1.6. Okay. Now, so we're going to follow this. We're going to use this to solve that problem. To calculate the speed, the slip, we need to check the relationship between the rotating magnetic field in the stator and the rotation of the rotor. You see that rotor in the field, in the stator, the magnetic field, if you played our previous class video, the magnetic field will be rotating at what we call a synchronous speed of 120 F over P. Okay, so 120 times 50 Hertz divided by number of poles. That's 1,000 RPM in this equation. But now, once this power is induced into the rotor will start rotating also. But the rotor is not going to rotate at the same speed with the rotating magnetic field in the stator. There will be a difference in rotation. Okay, that difference in rotation is what we call slip. So that means the slip will now be the synchronous speed, which is ns, minus nr, that is the rotor resistance, the rotor speed divided by ns. That's all. So since we have gotten ns to be 1,000 and we are given nr to be 970, then we can say 1,000 minus 970 divided by 1,000 times 100%. That will give you 3%. That is slip, or 0.03. Okay. And the next again is to calculate the rotor copper loss. Now, we don't know the resistance of the rotor, that copper bars. We don't know the resistance, but we can easily calculate that I squared R. But I don't know the resistance. So what we do is we're going to use this power flow diagram, okay, to calculate the rotor copper loss. How do you do it? First of all, now we have here, the power here is 50. Now into the stator, there will be some losses in the stator. So I'm going to remove these losses from 50 to give you 49. Now that 49 is a power air gap, the power that will cross over from the stator to the rotor. Okay, so, and then when it crosses over to the rotor, right, you can easily calculate the rotor copper loss. Now, what do? Just take the slip that you have calculated, multiply by that air gap power. That will give you the rotor copper loss. So you have S, which is this 3% as 0.03, times this P air gap, that will give you 1.47. Okay, like that. And did you know also that if you are asked to calculate the power developed in that rotor, you can even take also 1 minus S times that P air gap, which will give you now the power developed after you have subtracted, the copper loss of the rotor. In fact, sometimes we call it gross power. You know, the gross power right there on the rotor. Okay, but now we're asked to calculate rotor copper loss. So this is SP air gap. All right. So C, we want to calculate the output power. The output. So if I have 50 in here, then I will remove 1 kilowatt there. Okay, then I will remove the rotor copper loss. Now the remaining is what is going to be on the shaft. Okay, so in other words, if you got the shaft, I can remove the shaft power to get my P out. So because in other words, we can say that P in, this P in, will give you this P out plus this power here, plus this power there, plus all these losses. Okay, so now all the losses. So we can easily have like that, right? Say that now the P out here will be 50 minus 1 minus this one, because we've calculated this with 1.6. 1.6 and minus that also. So the rotor copper loss, the friction and windage losses, you remove them all. And then you are going to have this to be 45.96. Just check very well from your side if it's okay. This is just to make sure that this is yeah, so we got this with 1.47. That is the rotor copper loss, 1.47. So we have 1.47. 1.47. Yeah, this is the rotor copper loss. 1.47 is 1.6 for this one, and then this is 1 for that. Okay, so the power E minus all these losses will give you the output power. All right, and then from there you can calculate efficiency. Efficiency becomes P out over P in. Since we have now as our P out, I'll have 50 as our P in, then efficiency will now be 45.93 over 50 times 100 over 1. That will give you 91.86%. All right.